Welcome to The Explainer. Today, we are taking a massive leap forward. We're officially transitioning from standard prompting engineering into the much more advanced, highly specialized realm of hands-on model customization. Today's focus covers fine-tuning models in practice, drawing directly from Chapter 11 of the Developer's Guide to AI. You know, if you've been working with language models for a while, you've definitely realized that standard prompting eventually hits a wall. Maybe you keep running into those strict context window limits that cap exactly how much background information you can provide. I mean, if you try to just shove a massive training manual into a prompt, you're gonna hit token limits. And honestly, even if it does somehow fit, the model's attention completely dilutes over those super long contexts. Or perhaps you're just bleeding money on token costs for these massive repetitive system prompts. Or you simply can't get the model to natively adopt the highly specialized tone or vocabulary of your unique industry. When prompting just isn't enough, well, you actually need to alter the model itself. Okay, let's dive into our roadmap for today. First, we'll compare prompting versus fine-tuning. Then we'll establish a performance baseline, walk through the actual model training process, tackle the catastrophic forgetting problem, and finally, look at efficient tuning with PEFT and LoRA. Let's jump right in. Section 1. Prompting versus fine-tuning. We are moving from simply giving textual instructions to fundamentally updating a model's internal weights. Mechanically speaking, these two approaches are vastly different. With prompt engineering, you're really just crafting clever input instructions, right? You're relying entirely on the model's activations within its temporary context window. You give it examples and rules, but under the hood, the model hasn't permanently learned a single new thing. It completely resets the moment your session ends. Fine-tuning, on the other hand, permanently adjusts the neural weights, the actual mathematical connections in the AI's architecture. You're taking a pre-trained language model and training it further on a highly specialized dataset. Think about it like an inbox flooded with complex company emails. Prompting requires you to repeatedly explain what a support ticket looks like every single time you query the API. Fine-tuning actually bakes that knowledge directly into the model's foundational structure, so it natively recognizes the specific keywords, the structures, and all the little nuances of your specific business. So when resources and time are limited, prompting is absolutely your best tool. It's fantastic for general-purpose requests where you just don't have large volumes of custom data lying around. But when you need maximum performance, lightning speed, and deep domain adaptation, fine-tuning is for sure the path forward. Chapter 11 points out that to actually justify this switch, you generally need hundreds or even thousands of high-quality examples. But once you have that volume of specialized training data, fine-tuning lets you mold a model perfectly to your specific operational needs, which significantly cuts down on prompt length and inference costs in the long run. Moving right along to Section 2, establishing a performance baseline. This is crucial because we need to know exactly how generic models perform out of the box before we spend the time trying to improve them. Getting a baseline gives us a really clear mathematical benchmark to measure our engineering success against later on. Take zero-shot classification, for example. That simply means asking the model to categorize data without giving it any prior examples or context in the prompt whatsoever. We use zero-shot because it tests the raw, unprompted intuition of the model. For sorting specific corporate emails, a massive state-of-the-art model like Google Gemini might actually hit 100% accuracy right out of the gate, mostly because of its sheer scale and broad pre-training. But smaller, far more economical open-source models, they really struggle initially. DistilBERT sits at 69%, and Quan is way down at 58% before any fine-tuning even begins. They simply lack the massive parameter counts required to generalize instantly to highly specific niche formats. But by capturing this baseline data first, we know the exact performance delta we need to close. We know exactly what percentage we're trying to beat when we train our smaller, cost-effective models to essentially punch way above their weight class. Section 3. The model training process. Let's get our hands dirty and dive into the practical workflow of actually tuning a model. The training process consistently boils down to 3 essential steps. Step 1 is preparing the data. And listen, this isn't just dumping raw text into a folder. It involves gathering and carefully structuring thousands of examples into very specific formats, almost always JSON-L. JSON-L stands for JSON lines, where every single line in the file is a valid JSON object. This rigid structure ensures the training loop can perfectly map the prompt key to the completion key for every single example. Step 2 is fine-tuning the model itself. This is the computationally heavy phase where the actual learning happens. Here, developers have to adjust some critical hyperparameters. You have the learning rate, which dictates how aggressively the model updates its weights, and then you have epochs, which determine how many times the model cycles through the entire dataset. It's a delicate balance. Set your epochs too low and the model underfits, but set them too high and it literally just memorizes the data without learning the underlying patterns. Finally, step 3 is testing the new model. This is where you evaluate
evaluate your fine-tuned model against a held-out test data set. That is, data the model was explicitly prevented from seeing during training. If you don't hold data back, the model can essentially cheat by just recalling the training set from memory, which means you can't actually prove if your fine-tuning generalized its capabilities to handle brand new, unseen inputs.
Section 4. The catastrophic forgetting problem. We need to shift gears here, because regular fine-tuning definitely comes with some severe, hidden risks. The first major risk you'll run into is overfitting. This happens when a model learns the training data way too precisely, basically memorizing noise instead of recognizing the general patterns. Think of it like a student who perfectly memorizes the exact answers to a practice test, but completely fails the actual exam because the questions are worded just slightly differently. In a practical developer environment, you detect this by watching the loss metrics during training. A portion of your data is used purely for validation. If your training loss drops to near zero, meaning it is totally mastering that practice test, but your validation loss suddenly skyrockets, your model is overfitting. It's becoming wildly inaccurate on unseen data. At that point, you haven't trained an intelligent AI. You've just built a very expensive database lookup tool. But an even more dangerous issue is catastrophic forgetting. This occurs when retraining a model overwrites and completely erases the general knowledge it actually gained during its initial pre-training. Conceptually and mathematically, this happens because heavily updating the weights for a highly specific new task basically overwrites the complex web of parameters that previously allowed the model to understand general language in the first place. You are essentially destroying its prior representations just to make room for the new ones. So the crucial point is, without special techniques, teaching your AI a specific new trick might literally wipe its foundational understanding of basic grammar, logic, and context. Which brings us to a massive engineering dilemma. So, what does this all mean? How do we actually fine-tune a model so it masters our specific task without erasing its original knowledge and without racking up absolutely massive computational costs? That brings us to Section 5, Efficient Tuning with PEFT and LoRA. Let's enthusiastically introduce the real heroes of our story today, the techniques that make model training efficient, affordable, and most importantly, safe. First up is PEFT, which stands for Parameter Efficient Fine-Tuning. Instead of updating all the billions of parameters in a large language model, PEFT takes a totally different approach by introducing a very small number of additional trainable parameters. The core concept you need to know here is called freezing. You basically freeze the vast majority of the base model's weights, locking them down completely so they cannot be altered, and you only train this tiny new fraction of parameters alongside them. When we compare these two approaches side by side, it really highlights the hardware implications and shows exactly why PEFT is such a massive breakthrough. Regular fine-tuning, it requires huge, expensive multi-GPU clusters. In standard training, a 7 billion parameter model requires well over 100 gigabytes of VRAM just to store the 32-bit optimizer states, gradients, and full weight updates. That's enough to require serious enterprise-grade hardware. It's incredibly costly, and as we discussed, it leaves you highly vulnerable to catastrophic forgetting. PEFT, however, dramatically reduces those hardware requirements. Because you are only training a tiny fraction of the parameters, you drop that VRAM requirement by up to 90%. That means you can often tune these models on a single consumer-grade GPU. It saves massive amounts of compute and storage, and it perfectly mitigates catastrophic forgetting, because the frozen base model mathematically retains every ounce of its original pre-trained knowledge. Let's look at this quote from Chapter 11. Instead of taking the engine apart and rebuilding it, what if you could just adjust a few key components? This philosophy beautifully captures the engineering mindset behind one of the most popular PEFT methods out there, LoRA, which stands for Low-Rank Adaptation. It is all about achieving maximum leverage with minimal interference, preserving the foundational power of the model while gently steering its outputs to meet your specific needs. To put it into perspective, think of LoRA like a specialized custom chip added directly to your car engine's control system. Instead of physically tearing down a massive V8 engine to rebuild it for a different driving style, you just plug in a tiny computer chip that intercepts and adjusts the signals, letting you optimize performance without altering the core machinery itself. Mathematically, LoRA achieves this by decomposing large weight updates into smaller, lower-rank matrices. Instead of updating a massive 10,000 by 10,000 weight matrix directly, LoRA represents that update as the product of two much smaller matrices, like a 10,000 by 8 matrix and an 8 by 10,000 matrix. This completely changes the game. It drastically cuts the trainable parameters from 100 million down to just 160,000, all while still capturing the necessary learning signal required to adapt the model to your domain.
Now, what's really interesting about this is exactly where these tiny adjustments are made in the model's architecture. Notice that LoRA doesn't just apply these mathematical changes randomly. It specifically targets the attention mechanism projection layers and the feed-forward networks, or FFNs. Chapter 11 highlights exactly why these two targets matter so much. The attention mechanism is essentially where the model contextually understands the relationships and weighting within the input text. The feed-forward network, on the other hand, is widely considered to be where the model's factual knowledge is actually stored. By selectively tuning these highly specific functional parts of the architecture, you yield the highest possible impact. You allow the model to adapt its core information processing steps using literally just a fraction of a percent of the original parameters. So today, we've journeyed from the frustrating limitations of temporary prompt engineering right through the rigorous workflows of actual model training. We navigated the dangerous pitfalls of overfitting and catastrophic forgetting, and ultimately, we arrived at parameter-efficient fine-tuning with LoRA, unlocking the incredible ability to train on everyday consumer hardware. The barrier to entry has been permanently shattered. You no longer have to rely solely on massive, generic models that sort of work for your specific needs. Now that you have the knowledge and the tools to customize an AI model's engine directly, what specialized AI will you build first?